Okay, so this is Iteration Revisited. So this is a talk basically about a library that I've been working on for on and off for about the last year or so. And the talk really is in two parts. So the first half is about sort of the background and the motivation, why I want to do these things. And the second part is about the library itself. Okay, so that's what's on the menu for the next, well, a bit less than 75 minutes now. But hopefully that's okay. Is that okay with everybody? Yeah, a bit half-hearted, but you know, that's what you're gonna get, so tough. Too late to change it now. Okay, Iteration Revisited. Iteration Revisited, let's start by revisiting probably the first loop many of us ever wrote in C++. Something like this. Okay, so we've got some integer array, size 5, and then we've just got a for loop where starting from index 0, going up to the size, and then we're doing something for every element in the array. Okay, this is, you know, almost day one C++, probably the first code a lot of us ever wrote. But actually, there's more than one way we can iterate over a raw array like this. Perhaps if you came from a C background, you might have preferred to do something like this. Okay, so now we're initializing a pointer to the first element of the array. We're continuing iterating until the pointer is equal to the start of the array offset by size. We're bumping the pointer at each iteration, and then we're dereferencing the pointer to pass it to whatever the do something function does. Okay, so now of course you wouldn't actually write this today in C++. You might do something like this instead. I call standard begin, standard end, so this is quite nice. It means that for an array of known bound, we don't have to have this size parameter. It'll work it out for us. And in fact, you probably wouldn't even write this in C++ today. You might do something a bit more like this. So actually, I really like this. Well, I don't like the fact that we have to change lines, but I like this transition because actually all we've really changed is the variable name and the auto, and yet this suddenly looks quite a lot more modern. And yet you could go one step further and use a range for loop if you wanted to. A range for loop is basically syntactic sugar for something very much like this. Not quite exactly like this, but very similar. So what this little progression really emphasizes is that STL iterators are a generalization of array pointers. Okay, STL iterators are a generalization of array pointers. They take this idea of array pointers that are kind of the most powerful kind of iterators, contiguous iterators, and they generalize this to lower iterator categories. And this has been the case for, well, I mean, since the early 90s when the STL was first around, and then C++ 98, it became part of the standard library. This is what we've had for 25 years or more. This is really good stuff, right? There are a lot of advantages to this approach. It's really powerful. We can go all the way up to random access, contiguous. We can do sorts. We can write any sort of algorithm we can think of. We can probably do it with iterators. Iterators are low overhead. You can literally you can't get much lower overhead than a raw pointer, and you can use a raw pointer as an iterator. Right? This was particularly important back in the 90s when optimizers weren't anywhere near as good as they are today. You know, there's really low overhead to using iterators. If you go and look at this in Compiler Explorer, you'll see that generally all of the iterator stuff goes away, and you know, we get really optimized code. This one's maybe a bit more arguable, but we sort of have natural syntax. Now, a lot of people might say the iterator syntax isn't great, but it is based on the language syntax of pointers, right, which we kind of got to be familiar with anyway. So, you know, there's a kind of natural syntax for iterators. So, again, maybe that one's arguable. But there's sort of a fairly major con, that is a downside to iterators. And that is that iterators are just as dangerous as raw pointers. Okay, just as dangerous, just as unsafe. As soon as I start using words like dangerous and unsafe, we have to have a little bit of a digression to say, what do I mean by safety? What do I mean by safety? Well, a lot of, because the term means different things to different people, right? So there was a really great talk from Dave Abrahams at CPPCon last year. So Dave Abrahams is a very well-known name in the C++ world, co-founder of Boost, went to work for Apple for a long time, worked on the Swift standard library. Now he's back working on a language called Val at Adobe, aims to be a memory-safe language based around mutable value semantics. Sean Parent talked about it in his keynote on Wednesday. And Dave Abrahams, in this talk, is a great talk, by the way, you should all watch it if you haven't. Dave gives this definition of safety. He says, a safe operation cannot cause undefined behavior. Okay, that might be a little bit hard to read on the screen there, so let me blow it up just a tiny bit. A safe operation cannot cause undefined behavior, right? That's a definition of safety that I really like. Because undefined behavior, once we get language UB, all bets are off as far as our program is concerned, right? We can no longer reason about our program in any way because the compiler can pretty much literally do anything. We've all seen these crazy examples where there's some UB and then we end up with a completely different function being called to one we expected. We saw it if you saw the lightning talks, we saw some examples of this. Once undefined behavior occurs, we can no longer reason about our programs, right? So a safe operation cannot cause undefined behavior. Now, this doesn't necessarily mean that we get the right answer, right? We can still get the wrong answer, we can still have bugs in our program, but we don't get UB, so we can still sort of reason about our programs. So, okay, that was our aside. A safe operation cannot cause undefined behavior. So now let's take a little look at some iterators and try and decide whether iterator operations are safe or not, according to this definition of safety. I think you probably know the answer, but let's remind ourselves. Let's have a look at some examples. Okay, so what I'm doing here is I've got some range. I'm initializing an iterator to the past the end position of the range. So if you want to think about iterators as array pointers, this is one past the end of the array. We're allowed to do that by the language. What we're not allowed to do is what we're attempting on the second line here. So the second line, so the first line is fine, we can form the pointer, we cannot dereference the past the end pointer. Right? Again, if you think about array pointers, there is no object at this address. So dereferencing a past the end iterator is undefined behavior. Oh dear. Okay, well, what if instead of dereferencing the past the end pointer, we try and increment the past the end pointer? We call operator ++ on it. UB, yes, absolutely. Incrementing a past the end iterator is undefined behavior. Oh dear. So is decrementing a begin pointer. If we have a bidirectional range, we form a pointer to form an iterator to the start, we try and decrement that iterator. That's undefined behavior. So our out of bounds random access jumps, if you jump outside the bounds of a range, that's going to be undefined behavior, right? And again, you can think about this in terms of pointers. We can't form a pointer to some arbitrary address. That's just not allowed by the language. Okay, slightly more complicated example now. So here I've got a function miniter. It takes a const reference to a vector, and then it calls min element to return an iterator to the smallest value in this vector. Okay, so this kind of appears to be okay. Maybe, I mean, we don't really need it. We could call min element directly, but I guess people didn't like the .begin and .end, so they just wrote a wrapper function that takes a vector. Unfortunately, temporaries can bind to const references. So if our getVector function here returns by value, the reference is going to be initialized from a temporary. Min element is going to do its thing. It's going to return an iterator into the temporary vector. That's going to be stored in the iter variable. And then at the end of well, technically the full expression, but basically the closing semicolon, the temporary is going to be destroyed. And iter is going to be a dangling iterator. Essentially, it's a pointer into some deleted memory. And as soon as we try and dereference that pointer, bang, undefined behavior. So dangling iterators can occur surprisingly easily, and more or less any operation that we attempt to do on a dangling iterator is undefined behavior. I mean, technically you can destroy it and you can reinitialize it via assignment, but any attempting to actually use it in any useful, any meaningful way is going to be UB. So we can't, if we have a dangling iterator, we can't even ask, is this dangling? Because just asking the question is undefined behavior. All right? So this is really not great. All right, one last example, and this one is like particularly insidious. Right, who can tell me what the problem is here? I'm sorry. Accessing the iterator after pushback. Yeah. So iterator invalidation is the problem. But it's okay, because this is guaranteed to happen, right? This is always going to be a problem. So the first time we run this code, we're going to know it's bad. No, because this is particularly insidious because we are iterator, or iter, again, if we want to think about it in terms of pointers, iter is like effectively a pointer to the start of the vector's internal array. Then we're going to push back, and if this pushback call happens to cause a reallocation, then internally the vector is going to allocate a new array, it's going to delete the old array, and we're left with a dangling pointer, or a dangling iterator. And again, as soon as we try and use this dangling iterator, so in the while condition, we're attempting, or possibly attempting to compare a pointer from one deleted array to a pointer to a completely different array. This is UB, according to the language. So, you know, we can't even, as I say, we can't even ask an iterator, are you valid or not? And as I say, this one is particularly insidious because most of the time this is going to work. And you know, this could be in your code base for like 20 years. And then one day you recompile and your standard library happens to have changed the growth properties of the vector so that now pushback is an allocation where it never used to be. Or maybe somebody's changed a single line 1,000 lines of code away, so now the vector is a slightly different size to what it used to be. And now we're hitting the UB case, whereas our code worked perfectly well. It was erroneous, but we didn't know it for, you know, however long. So this is really bad. And, you know, iterators can become dangling in non-obvious ways because this is not obvious. If you are a C++ newcomer, like a lot of people in the room answered, but that's because I'm at a C++ conference with loads of really experienced C++ devs, right, who know about this problem. But the only way you know about this problem is either because you've been bitten by it or because somebody's told you, right, or you read it in a textbook or something. There is no way that you can just by inspection look at this and go, oh no, that's problematic. You have to either know how vector works behind the scenes or somebody has to tell you that this is problematic. So this is just all part of the C++ experience, right? This is how you become a senior dev. So our statement was a safe operation cannot cause undefined behavior. And yet, most iterator operations can cause UB. And so really, and these are harsh words, but really we have to conclude that STL iterators are a fundamentally unsafe abstraction. They're based around raw pointers. Raw pointers are not safe in C++. STL iterators are a fundamentally unsafe abstraction. Okay, so can we come up with a different abstraction that is perhaps safer? Which is, I'm going to say yes, because that's kind of the point of this talk, right? But let's build up to it. Okay, what would such an abstraction actually need to be able to do? Okay, so let's go back to our example using iterators and a for loop. Or really any external iteration scheme needs to be able to do 4 things. We have 4 fundamental operations that any iteration scheme needs to be able to do. So first of all, we need to be able to initialize some iteration state. So with iterators, our iteration state is encapsulated in this iterator object. But really for any iteration scheme, any external iteration scheme, we need to be able to initialize some iteration state. We need to be able to check whether iteration is complete. So again, with iterators, we do this by comparing it with the past the end iterator or with sentinels in C++20. But fundamentally, we need some check operation. We need to be able to read the element corresponding to our state. If we can't do that, then what's the point of, what are we even doing? We need to be able to read the element. We do this with dereference operation for iterators. We need to be able to read. And then finally, we need to be able to advance our iteration state. Right? We need to be able to say, okay, now I want to look at the next element in the sequence. Okay, 4 operations. Initialize, check, read, advance. Okay, and this is not new, this is very well known, this has been known for decades and decades. In fact, if you think about the very syntax of the for loop in C, it's kind of designed around these 4 operations, right? So like the for keyword is really just syntactic sugar in C for a while loop. That helps you do these 4 operations. So our iteration scheme, obviously it has to do these 4 things, but what's actually quite interesting is that it has to do these 4 things, but these don't actually need to be 4 separate functions. We can, in fact, fuse together 2 or more of these operations in a single function call. And if people are familiar with Rust iterators, Rust actually fuses together the check, read, and advance operations into a single function called next. And in Rust, next returns you what in C++ terms we call it an optional, returns you an optional containing the element. Every time you call next, it gives you an optional with the next element, until eventually it returns you an empty optional, which signals that iteration is complete. Okay, so that's the Rust iteration scheme kind of in a nutshell. There are advantages and disadvantages to this, the primary advantage being it's very much simpler for both producers and consumers because there's only really one function to worry about. The downside is that we lose some expressive power by fusing together these operations. There are algorithms that you can't write or you can't write as efficiently if you've got fused operations. So if we're looking for an iteration scheme that's going to replace iterators, we really need something that does these 4 operations separately, right? Otherwise, we're going to lose some expressive power. So if you're interested in this stuff, Barry Resin has this absolutely amazing talk. It's honestly, it's one of my favorite, I think one of my favorite tech talks of all time, but certainly on the subject of iterators and ranges and stuff. So he's got this talk where he compares C++ iterators, D ranges, Rust, also mentions Python, C#, Java, all sorts of things. Compares and contrasts this. I think Timur mentioned this in his talk yesterday as well. This is a really great talk. So if you're watching this on YouTube, once you've finished with this one, go and watch Barry's, because it's great. So, okay. Right, where are we? We know we want to have a new iteration scheme that is safer than using iterators, and we know the 4 operations that we need to perform. And it turns out there is an iteration scheme that you are already familiar with that does all of these things in just the way we like. And I guarantee you are all already familiar with it. I know that for a fact because it was the very first slide of this presentation, right? It's not exactly the same as the first slide, but it's iterating via indices. So when we're iterating via indices, we are initializing some state. In this case, it's the integer index. We have our end check. We're checking that our index is less than the size of the vector. And now we define our read operation to be vec.at. Okay, we define our read operation to be bounds checked. And then finally, we define our advanced operation to just increment the index. So let's have a go at taking our iterator examples from earlier, our bad examples, and seeing what happens if we substitute the iterator operations for our newly defined operations using indices. What happens in these cases? Well, this was our first example. So we started off, we had an iterator, and we initialized it with standard end. The equivalent with indices would be to initialize your index to the size of the vector, right? But now, if we perform our read operation, this was the dereference with iterators, now we're calling vec.at. Vec.at, it's bounds checked, and this is not undefined behavior. This is going to throw an exception. Now, maybe exceptions aren't what you want, but it's well defined, right? It's not UB that we would have gotten in the iterator case. No UB. What about the second example? So now we've got our past the end index now, and now we're incrementing the past the end index. So this was UB when we tried to do it with iterators. What happens when we try to do it with indices? Well, I've got some size t, and I'm calling operator ++ on it, and that's it, right? This is fine. This is fine. In the incredibly unlikely case that the size of the vector is like max of size t, which good luck doing that on a 64-bit system. Even on 32-bit, really, I don't think you can actually allocate a vector that size. But still, even then, you know, the size t is going to wrap around. It won't give you the right answer, but it's not undefined behavior. So incrementing a past the end index is fine, assuming we're using unsigned indices, or if we're using signed indices, we have some sort of checked add. So what about our min elements problem? So if we imagine we've got some min index function, it's only a few lines of code, but the lines of code aren't really relevant. What's important is the interface, right? So we've got our min index function now. Previously, it was min iter. Our min index function now, and it's taking a const reference to a vector and returning the index of the minimum element. And so what happens when we call this with some temporary vector? Well, okay, we find the minimum index. We store that in the IDX vector, in the IDX variable. The vector gets destroyed, and then what happens? Then we're just sitting there with a useless size t, right, that we can't do anything with. We can't do anything with it because in order to perform our read operation, we'd need the original vector still around. So dangling indices, if you like, are safe by design. We can't, I mean, we can have a dangling index, but all we're doing is holding on to some integer value, right, which is fine. It's not dangerous, it's not problematic. So this was our final example. This was the really hateful, really insidious one, the one that is absolutely undiscoverable. Okay, so now we've replaced our iterator operations with index operations. What happens? We initialize our index to the start of the vector. We perform a pushback, and then everything's fine because our index hasn't been invalidated. Right? And okay, we can still, you know, in this particular example, we don't get index invalidation. We can still have index invalidation if you're holding on to index 100 and you resize the vector so that it's now size 50. You know, your index is invalid. But next time you call the read operation vec.at, that's going to be caught by the bounds checker. Right? So index invalidation problems, this really horrible, undiscoverable problem that can lurk in our code bases for decades, is no longer undefined behavior. And any invalid index is going to be caught by the bounds check on our next attempted read. So index-based iteration dramatically reduces the potential for UB. So we saw that when we were using STL iterators, which are effectively modeled on raw pointers, that almost any operation had the potential to be undefined behavior, in particular because we could get dangling iterators where literally anything we do with it, other than destroying it, is UB. Index-based iteration dramatically reduces the potential for UB, but it's still just as powerful, right? We can do random access using indices, right? Any algorithm we wanted to write using iterators, we could, in principle, write using indices instead. In fact, if you go and look in algorithms textbooks, very often they are written using indices, and you have to go back and translate that into it. I don't know if anybody's done that, but yeah. Okay, so if iteration by index is safer, what if, instead of doing what the STL does, which is to generalize the idea of iteration by pointer, what if we were to generalize the idea of iterating via an index? What if, sorry, go ahead.
What about node-based containers?
That's a tricky one. We'll come back to that. Sorry, the question was what about node-based containers? It's a tricky one. We'll come back to that somewhere near the end, yeah. So what if what if somebody were to write a library that took this idea of generalizing iteration by index rather than iteration by pointer? What if somebody did that? Wouldn't that be wonderful?
You did that.
You did that. Yeah. Well, I did that as well. So my library is called Flux. The name is not in any way relevant. The important thing about the name is that it's got an X in it. So it's all like cool and mysterious. So the library is called Flux. The URL is there. And it's a C++20 library, and it's exploring these ideas of index-based iteration as opposed to pointer-based iteration. So Flux aims to provide much improved safety by default compared with using STL iterators. Improved ease of use and fewer gotchas, right? So if you've seen any of my talks before, I know quite a bit about ranges. So, I know the things that maybe the sort of rough edges, the things that aren't so great. So Flux aims to sort of smooth off some of those rough edges and make things perhaps, hopefully, a little bit easier to use in some respects. Flux aims for equal or better runtime performance than code using C++20 ranges. So if you can afford to use ranges, you can afford to use Flux. I'll talk a bit more about performance towards the end. And also offer compatibility with existing STL code. So the STL, iterators, ranges, ranges are newer range adapters, but iterators have been with us for a very long time. There's an awful lot of code out there that's using it. We can't just reinvent the world. That's not going to work. We have to offer some sort of compatibility story. So we'll have a little look at that as well. Okay. So let's look at our iteration operations in Flux. We talked about our 4 operations that we have to do. We have to initialize, check, read, and advance. So how do we do those things in the Flux library? Okay, so our initialization operation in Flux is a function called first. So I couldn't call it begin for obvious reasons. So what's a synonym for begin? It's first. So we have this function first. You call it on some sequence, and it returns you an object called a cursor. And a cursor represents a position in a sequence. A cursor is a generalization of the idea of an index. And actually, originally, when I was writing the library, I called these things indices, but the word index has strong associations with like an integer, and cursors don't necessarily have to be integers, but it does so happen that for contiguous sequences, then it is literally just an integer index. So in any of the following slides, when you see the word cursor, if you just mentally substitute the word index, you're going to understand what's going on. Okay, so first returns you a cursor representing the sequence position, representing the position at the start of the sequence. We have this function isLast. This is our end check. And what this does is it says to the sequence, please can you tell me whether or not this cursor is a past the end cursor, whether I have finished iterating. We have our read operation. In Flux, this is called read_at. So read_at says to the sequence, please will you give me the element corresponding to this cursor position. Okay? And then finally, we have our advanced operation. This is just called inc. So this takes the cursor by reference and it bumps the cursor so that it now points to the next position. Okay, so these are how we spell these operations in Flux. You can see they sort of closely map onto the equivalent operations on integers, on iterators, sorry. And a type which provides these four operations, and we'll see a bit later on how you provide those operations, but a type which provides these four operations models the sequence concept. Again, so I didn't want to reuse the term range because that would get really confusing. So in Flux, these things are called sequences. And again, sequence is also an overloaded term, but you've got to call it something, right? So by default, sequences are assumed to be single pass. That is, once we have incremented a cursor, we can no longer use the elements that have already gone, the equivalent of input ranges in the STL. Of course, we also have multi-pass sequences. So multi-pass sequences are those which allow for simultaneous iteration by multiple cursors. These are the equivalent of forward ranges in the STL. So this allows you to write another class of algorithms with multi-pass sequences. So multi-pass sequences require that their cursors are regular types. And a regular type, if you are not familiar with it, is one that is default constructible, copyable, and equality comparable. So multi-pass sequences require cursors to be regular types, and so we can always copy the cursor for a multi-pass sequence. We can always sort of save where we are while we're iterating. And we can also compare them for equality. We can say, do these two cursors represent the same position in a sequence? So in almost all cases, cursors for single-pass sequences should be move only, right? If they are copyable, that's probably that's a very questionable decision. However, I wasn't really comfortable with requiring something to be move only. Requiring something to be non-copyable just seems really strange. So there is an opt-out. If for some reason you have a single-pass sequence but the cursors are copyable, then you can opt out and you can actually say, no, I'm not multi-pass. But it turns out that if you do things the intended way and you make your single-pass cursors move only, then you don't really need this. So we've got single-pass sequences, the equivalent of input ranges. We've got multi-pass sequences, the equivalent of forward ranges. We can go further. We have bidirectional sequences. So these are multi-pass sequences which additionally allow cursors to be decremented, to be moved back one place. Okay, so we've got the function fluxDec, the opposite of inc and dec. So we can decrement a cursor to go back one spot. And then finally, or nearly finally, as you might imagine, we've got random access sequences. So these provide some additional operations as well. We've got another overload of inc, which this time takes an offset, signed offset, so we can go arbitrary distances either side from where we are. They provide a distance operation, which will tell you the distance between two cursor positions. So, how many times do I have to call increment to get from here to here? And also the cursors for random access sequences must be totally ordered. That is, we have to be able to say, is this cursor position earlier or later in the sequence than this cursor position? Okay. And then we also have contiguous sequences. So these are random access sequences that are backed by some like in-memory array. This allows like low-level operations, memcopy and things like that. So these have obvious analogs to the existing ranges categories, right? There are a couple of other concepts that we have that are also, they also have analogs to C++20 ranges categories, but you might be a bit less familiar with them. So in Flux, we have what we call bounded sequences. So our end check operation, we had this isLast function. So this means that actually sequences don't need to be able to provide a pass the end cursor, right? And this is really quite useful for doing writing certain kinds of sequences. But actually, a lot of sequence implementations can provide this pass the end cursor in constant time. Those that can, we call them bounded sequences. And there's a function called Flux Last, the counterpoint to first. So first gives you the cursor to the start, last gives you the cursor to the end. So in particular, if you want to reverse a sequence, then not only do you need bidirectional iterators, but you also need to know where the end is so that you can start going backwards from there. We have sized sequences, which allow accessing the number of elements. If we know the number of elements ahead of time, then that's called a sized sequence. And again, so bounded sequences, if you're familiar with common ranges in C++20, that's pretty much the same as what a common range is. And we also have sized sequences that tell us, that know ahead of time how many elements they have. And then finally, there's something that isn't in ranges. It's infinite sequences. So this is, these are sequences that sort of guarantee that they're never going to terminate. Okay, so they have like a compile time marker that says like, I'm just going to keep iterating forever. Turns out infinite sequences, not quite as useful as I thought they were going to be when I first put them in. So they might disappear at some point, but you know, they're there at the moment. Sorry, do you have another question?
So if I increment past the end, like way past the end, and then decrement back into the range, is that fine in Flux?
If you increment, decrement, yes, you're going to be okay. Yes. Okay, so these concepts in Flux that we have, these operations that we have natural analogs with the STL operations, with the STL concepts. And so we can actually, with not all that much work, take STL algorithms and modify them to work with these Flux functions. And there are an awful lot of algorithms in the STL, and you know, I haven't implemented all of them in Flux yet, but we're doing pretty well. So we've got quite a few algorithms going on in Flux already. This is as of June 23, so if you're watching this at some point later on YouTube, there might be more. So we've got an awful lot of algorithms that you can apply to your sequences and you know, get some result out. Rotate not there yet. But it's not a problem, because you're going to see, as you'll see in a minute. Okay, so again, if you've seen any of my talks in the past, you'll know I'm a really big fan of C++20 ranges stuff. All these views, all these range adapters. And so implementing the C++98 equivalent algorithms is all very nice, but I wanted to go further. I wanted to be able to do all of the things you can do with C++20 ranges. I wanted to be able to do that in Flux. So like C++20 ranges, Flux has a variety of sequence adapters, equivalent range adapters, views as people call them. In Flux, we have sequence adapters that perform lazy evaluation. And typically, we compose these into pipelines. So exactly as we do in C++20 ranges, we can form Flux pipelines. So typically you'll have some source sequence, a vector or whatever it may be, maybe some generated sequence like an iota or something like that. You'll have some source sequence, you'll pass it through 0 or more adapters, and then finally you'll have a call to an algorithm which will actually perform the iteration. Okay, so your final algorithm call, it might be a named algorithm provided by Flux. It might be one of these things we've seen. It might be an algorithm that user-written algorithm that is in your own code base. It might be an STL algorithm, as we're going to see, or it might be a for loop. Because here's Tristan's law. I don't have a slide on this because otherwise Connor will put it on one of his slides. So I'm just going to say it. Tristan's law, right? Every for loop in your program is an ad hoc, unnamed, unspecified algorithm on some sequence. Right? That doesn't automatically mean it's bad. Right? Maybe it is genuinely like one-shot code. Like I don't care. I'll just do this once, right? Because it just does what I need. It doesn't automatically mean it's bad, but it does mean, maybe you should think about, can I use a named algorithm instead? All right. So let's have a little look at what a Flux pipeline looks like. So we've got some vector called vec, and what we want to do is we want to find, and again, this is one of these contrived problems that you always see on slide code, so apologies for that. But what we want to do, for some reason, we want to find the maximum of the squares of the even numbers in this vector. Okay, we've got a vector of integers. We want to find the maximum of the even, maximum of the squares of the even numbers in this vector. Okay, so first of all, we're going to iterate over a reference to the vector. So in Flux, we want to be very clear about whether we're using references or whether we are copying the vector, whether we're moving the vector. So we're going to be explicit about the fact that we are referencing this vector. And then we're going to add a filter adapter. So right away, you can see a bit of a difference to ranges is that Flux uses member functions for chaining. This is, I'll be honest, there's no real technical reason for this. I could have used pipes like ranges does, would have been quite, well, not easy, but it's certainly very doable. But really, I just really much prefer the way that it reads if you use member functions, if you use the dot syntax. I think it just makes your source code look a lot more readable, a lot more understandable to other people coming and reading the code. So Flux uses the dot syntax. So we're going to pass this through a filter adapter. Then we're going to pass it through a map adapter, which is going to square each element. So the STL calls this operation transform, but literally every other library and language under the sun, as Connor will tell you, calls this operation map. So we call it map in Flux as well, right? So the map operation is going to square every element. And then Flux has this algorithm called max. And in Flux, you can just chain your algorithm call onto the bottom of your pipeline. Okay, so we can call our max algorithm, and this is going to find the maximum value in this adapted sequence that we've got. Okay, so can people see what's going on there? Yeah? Sorry, a question?
Like if you want to find the max, though, I mean, you don't need to square it.
Find the max and square the max instead.
What if we've got negative numbers? So the question is, well, why are you squaring if you're just trying to find the max? Well, first of all, because this is example code, which is the main reason. But also, I guess, if you had negative numbers, right? Yeah, and don't talk to me about absolute values, right? Anyway, people can hopefully see what is going on, right? It reads clearly what's happening. There is actually a bug here, though. And I don't just mean the missing semicolon. There is a bug on this map.
What if it's empty?
What if it's empty? Absolutely, yeah. What if vec is empty, or what if vec only contains odd numbers, so that after the filter, the resulting sequence is empty? What happens then? Good question. So actually, does anybody know, there is an equivalent standard ranges max algorithm that you can pass a range into and it will give you the maximum value. Does anybody know what happens if you pass an empty range into standard ranges max? UB, yes, well done. Yeah, absolutely. It is undefined behavior for standard ranges max. We want to avoid undefined behavior as much as possible. So actually, the max operation in Flux returns you an optional. And if the input sequence was empty, then the optional is empty, and otherwise the optional contains the maximum value. So we have to, as the user, decide how we want to handle empty sequences. And so in this case, I've just decided that the easiest thing to do is, if the sequence is empty, then the maximum is 0. Yes, Min?
I was thinking, since your algorithms are all member functions, how do you add your own algorithms?
So the question is, since the algorithms are member functions, how do you add your own? Well, first of all, you can, there are two forms. So there's a member function form and there's a free function form you can use as well. But also we have an apply function, so you can provide your own algorithm at the end of a chain if you want to. I don't have a slide with that as an example, but yeah, we handle the case. Yeah. Okay, so this is what the sequence adapters look like. We've got a whole bunch of sequence adapters in the Flux library. Again, this is as of right now. If you're watching this later on YouTube, there are very likely to be more because I love these things and I love doing them. So we got lots and lots. I thought we had parity with C++23. It turns out that thanks to Connor's talk, I know there's one I've forgotten. But we have, apart from one, all of the ones that are in C++23. I think all of the ones that have been proposed for 26 and a few more besides. Sorry? That's called chain in my library, because that's a better name. Okay. We'll get to that at the end. Okay. So this, can't go back to it, but that's an example of what things look like from the consumer side, right? If you are, you have some sequence and you want to perform operations on it, that's kind of what your code is going to look like. But one of the things I want to do in Flux is to make it easier to work on the other side as well, that is the producer side. So if you have some type and you want to implement the sequence protocol for that type. So I don't know if anybody has ever tried writing like a fully conforming, fully generic range implementation. Yeah, it's a lot of fun. So one of the things I wanted to do in Flux was to make this easier. So we've got a little example of implementing the Flux protocol for a type. So we're going to use this type myArray. It's pretty much the same as standard array, but standard array already has a sequence implementation. So we're going to implement the sequence protocol for myArray. Okay, so the way this is done in Flux is by specializing this class template, Flux sequence traits. So this is a pattern you might have seen in other libraries, standard formats, or the format lib, various boost libraries do things like this as well. So we provide a specialization of the class template Flux sequence traits. Okay, so we've got an alias self-t, just save space on the slide. So that's just an alias for my array. And then within the body of this class, we need to provide a minimum of 4 functions. And I think you can guess what those 4 functions are. Okay, so the first thing we need to do is provide an implementation of first. So this is a static member function that takes as its first argument the sequence type, and it returns whatever the cursor type for this sequence is. So in this case, our cursor type is just a size t. And so we initialize our size t to 0. That's the first index. So this is pretty simple. We need to implement the isLast function. So what this does is it takes the sequence, it takes the cursor, and it says, is this cursor out of bounds? Or rather, is this cursor like an end cursor for this sequence? So for our particular implementation here, we don't actually even need the array because it's like a static property, but we just compare it, we say, are we greater than or equal to the size of the array? Increment operation, again, for this particular example, very simple. All we do is we bump the size t, increment the size t. And we can be fairly sure that our stack array is not going to be max size t. That would be a bit tricky. And then finally, we have our read operation. This is a little bit more complicated because we want to handle both const and non-const access. So we take our first parameter as an auto ref, so that we can have both a const my array and a my array, a non-const that is, and we return decal type auto because our return type is either going to be tref or tconstref. Okay, but we can write both of these implementations in one function. And the first thing we do in this function is we perform a bounds check. Okay, we have a function called flux bounds check. This does exactly what it says on the tin, right? It's kind of an assertion that this condition is true, and if not, it's going to, well, by default, it's going to terminate your program. You can also configure the library so that it throws an exception instead, in case you want to do cleanup on the way out. Okay, but it's going to print a message and do all the right things. So having got the bounds check out of the way, we can then access the array element at the cursor position. Sorry, the data at the cursor position. Okay, so in order to, and that's it, right? So in order to implement the sequence protocol, we have to provide 4 functions. And having done that, if you were to copy and paste this, you would now be able to use this with all Flux sequences, sequence algorithms, with all Flux sequence adapters, right? Or at least all the ones that don't require higher, bidirectional or higher. So this is a Flux sequence. In fact, because our cursor type, size t, is a regular type, this is in fact a multipass sequence all by itself. Oh, yeah. So there's actually, that example, we use this external struct class template, Flux sequence traits. There's actually another way you can do this. If you are the author of a type and you don't mind modifying the definition of that type, you can actually write your sequence implementation in line as part of your class definition. Either or, they both work exactly the same. This tends to be kind of a bit tidier. Otherwise, you have to like close and reopen namespaces, and it's all a bit messy. But with this, if you have a public nested class called Flux sequence traits like this, then you can write your sequence implementation in line. So implementing the sequence protocol, at least in my opinion, because I wrote it, at least in my opinion, is considerably easier than trying to implement the full range API, where you've got to have, you've got to write an iterator implementation, which goodness knows how many how many operator overloads that needs for, like, if you're going all the way up to random access. It's a huge list. I can't even remember how many there are. Lots and lots. And then you've got to write a begin and end that return you the start iterator, the end iterator. And then you think, oh no, I need a begin and end const. And then you're like, oh no, now I've got to write a const iterator type. And so you go and end up and you template your iterator class, and then you've got to worry about converting constraints. Anyway, it's a nightmare, right? So this is, at least in my opinion, considerably easier to implement versus STL ranges, and even more so for higher sequence categories. So if you wanted to make this a bidirectional sequence, there's one more function you write. You write an implementation of dec. If you wanted to make this, after that, random access, there are 2 more functions you need to write. Okay? So none of these endless operator overloads. Another thing you might have noticed is there's no, and I just touched on it, there's no iterator versus const iterator confusion. Right? The same cursor type is used for both const and non-const access. And if you think about how indices work, right? If you have like an index into a vector, it doesn't matter if the vector's const or not. It's the same index type, right? So we don't have, there's no such thing as like a const cursor in Flux. We use the same cursor type, and whether you get const access or not, it depends on whether the thing you pass to read at is const or not. Okay, how am I doing for time? We started a little bit late, but I'm okay. So, ranges compatibility. So when I started talking about the library, I mentioned that there is an awful lot of ranges code out there already, and we can't just pretend it doesn't exist. I can't just say, right, forget about that, start using Flux. We need to offer some measure of compatibility with existing STL code. So to this end, every C++20 contiguous range is automatically a Flux contiguous sequence. So if you have a contiguous range, you can just, without doing anything whatsoever, you can just use it with all of the Flux algorithms, all of the Flux adapters, all of that stuff is just going to work. We have a blanket implementation for every C++20 contiguous range. The reason we can do this is because contiguous ranges are sort of cheaply indexable. We can get the raw pointer, and then we can use an index into that raw pointer, and we can do the bounds checking. So this all just works. Right, so this covers vectors, arrays, strings, string view, span, all of these things. Right? All of these things that you really want to be using in your code. Right? So any contiguous range, automatically a Flux sequence. There are other kinds of ranges, sadly, that people use that are, sometimes people use containers that aren't vector, apparently, which is weird, but apparently people do it. So for other ranges, we have this function flux from range. And what this does is it takes your range and it wraps it in the sequence API, the thing we just saw, implements these functions. But it implements these functions by calling the equivalent functions on the iterator. It sort of uses, almost, not quite, but nearly uses the iterator as the cursor type. And so because we're calling the iterator functions and because the iterator functions are themselves unsafe, we can't provide bounds checking when none exists in the underlying thing. So from range it kind of reduces, takes away kind of what Flux is trying to add, but we have to be pragmatic. So you can use from range, slightly reduced safety guarantees compared to native sequences, if you like, but it's no worse than using ranges directly. So you're not losing anything compared to using ranges algorithms. So if you have existing ranges, you can use them with Flux, either just without doing anything if they're contiguous, or by wrapping them in this from range function, or by, if you really want to, implementing the sequence protocol kind of natively. We can also go in the other direction. So if you have a Flux sequence, every Flux sequence is a C++20 range, right? Every Flux sequence provides STL-compatible iterators. So if you have some Flux sequence you've built up with, some base sequence and a chain of adapters, you can use that with C++20 range algorithms, even with C++20 range adapters, if you want to. And yes, it means you can use Flux sequences with range for loops as well. So I think this is actually really nice. How does this work? Well, we have this iterator implementation that kind of holds a pointer to the sequence and the cursor, and then it implements all of these endless operator overloads that iterators need. And it does all that by calling the equivalent Flux code, as you can see on the screen there, for example, for operator ++. Okay, so, this iterator is holding a raw pointer. This is kind of unsafe. It's prone, you can dangle and everything, but hey, it's iterators. We're used to that. So we have two-way ranges compatibility as well. Okay. last little section now. There's something I need to address. There's something I've skirted around. We've all just nicely pretended it's not there. That's this guy. So let's talk about performance. Let's talk about performance because Flux uses bounds checking for whenever it's necessary to ensure that as much as we possibly can, we avoid undefined behavior, particularly in our read operations. Right? So the read operations are bounds checked, as we saw right at the beginning when we were looking at the vector example. So this is kind of worrisome for a lot of people. Well, can I afford this bounds checking? It turns out compilers are just mind-blowingly, amazingly good at eliding bounds checks, right? Just breathtakingly good at it. And almost any language you can think of that was designed in the last 20, maybe 30 years, maybe longer than that, they use bounds checking kind of universally. Like C++ and C are really the exception in the fact that it's completely unsafe. And so actually, optimizers are incredibly good at recognizing these patterns. And just, if it can prove that the bounds check is unnecessary, it's going to remove it. So I've got a little example, courtesy of Mac Compiler Explorer. This is going to be a little bit hard to see unless you're in the front row. But we've got just a little loop that's just going through a vector and counting how many even numbers are in that vector. So this is like really kind of basic code, just doing this loop using a for loop. And then we've got the equivalent code in Flux. We use this macro. It's mostly used for testing. It's a macro called Flux for that it just manually uses first read at is last, etc. Manually uses the Flux primitives for doing iteration. And again, it might be a little bit hard to see, but fundamentally, the inner loop kind of has the same shape. There's some red and some green because the compilers decided to put things in different registers, but there's no kind of major difference. And I tried benchmarking this, and it's just, the only difference is noise, basically. Sometimes one was faster, sometimes the other. I couldn't get consistent numbers. But basically, for examples like this, and most actually really in general, if what you're doing is beginning at the beginning and ending at the end, you very often don't need to worry about the overhead of bounds checks. But actually, things are even a bit better because this implementation, the one you just saw, uses this macro Flux for, this is, as I say, really a macro that I use for testing internally. It's not really intended for end user code because idiomatic use of Flux, if you like. I don't know if you can have idioms in a new library, but I guess I get to decide what they are, right? So idiomatic use of Flux, we'd use a named algorithm where one exists. And in this case, we want to count how many even numbers there are. That was what we were doing. So we got this function, Flux count if. So what happens if we, instead of using the Flux for macro that we were using before, we use count if? Well, now we get precisely 100% bit for bit identical code in both cases. The only thing that's changed is the function name.
That's awesome, yeah.
All right, so what devilry, what black magic is going on here, right? What's changed? Well, Flux has this really neat trick with internal iteration. Okay, so the Flux sequence protocol has an extra optional customization point, which it's called for each while. A bit of an unwieldy name, but it describes what it does. So you provide it with a predicate, and it's going to iterate over the sequence in the best way that it knows how, and test every element against this predicate, and as soon as the predicate returns false, iteration finishes, and it actually returns you the cursor position at which iteration finished, or if we got to right to the end, it returns you the past the end cursor. Right, so this is actually exactly the same algorithm as find if, or specifically find if not, except that for each while, the reason it has a different name is because you're allowed to provide a stateful predicate into the Flux version. Right, that's why it's not called find if. That's why it's got this unwieldy name instead. So as I say, this instructs the sequence to perform internal iteration until the predicate returns false. And it turns out that many sequence implementations, and in particular many sequence adapters, can perform internal iteration more efficiently than just calling isLast, increment, read at over and over again in a loop. Right? Internal iteration can, in many cases, be performed more efficiently. And actually, the more you build up a pipeline, the more this sort of multiplies. Because if you kind of think about what you have to do when you've got a whole pipeline of adapters, this is true in Flux and in ranges and in most other libraries that use this pattern, the Rust iterator library as well, right? You have your lowest level adapter has to call isLast on the next one in the chain, has to call isLast in the next one in the chain, etc., all the way up until you get to your base sequence. And the same for read at, and the same for increments. Now, all of these things can be inline, but this kind of puts pressure on the optimizer. And, you know, in terms of algorithmic complexity, it's okay, we're still linear, but it puts pressure on the optimizer, and in many cases, it sort of befuddles it so it can't produce code that is as nice as via for each while with internal iteration, where effectively we get kind of a chain of embedded lambda functions because we provide a modified predicate to the next sequence in the chain. Basically, we get better code generation. And we can write many, many, many algorithms in terms of for each while. So we can write a fold, find if, min, max, any, all, none, count, countif, loads and loads of algorithms we can write using this for each while pattern. And what this means is, because Flux has this neat trick that it can do for certain algorithms, for certain algorithms, Flux can actually generate much better code in quite a lot of cases than the equivalent C++20 ranges pipeline. Okay, so a little example of that. I've got this pipeline where we're taking some vector, we're applying a filter, we're applying a transform, and then we're calling standard accumulate. So this is the ranges code. And then we've got the equivalent Flux code. So again, we're taking a reference to our vector, we're filtering, we're mapping, and then we're calling sum, right? Because that's easier to spell than accumulate. And again, for the people in the front row, we'll be able to verify that the Flux code on the left, oh, there's an awful lot more code. But look very carefully at what those are, and there are a whole bunch of AVX instructions. Because on the left-hand side, with the Flux code, with this internal iteration, the compiler's been able to see through our code much more easily, and it's been able to vectorize this loop, whereas for the ranges code on the right, although it's superficially simpler, this is not vectorized at all, and so you're likely to get much better performance. I'm getting the thumbs up from Mr. Godbolt in the front row, so that makes me happy. So you're likely to get much better performance. So, very last little bit now, avoiding bounds checking. Sorry, yeah.
So the for each while thing, as you go through a chain, it's just one call for each while, but just with an alternate predicate, or?
So how does this work? I did actually have a slide demonstrating this, but I knew I was going to be pushed for time, so I cut it out. But maybe I'll be able to find it for you afterwards. But yes, basically the question was, does for each while, it works effectively by for each while calls for each while on the next thing in the chain and provides it a modified predicate, which calls for each while with a modified predicate. And it turns out that this leads to, in many cases, better code gen. than a naive loop would. Okay, so if you are in the happy case where you're using an algorithm that can use this for each while, that's great because for each while it does internal bounds checking. We're in control of the iteration. We don't need to do any bounds checking because we know nobody's going to be messing with our cursors and making them jump out of bounds, right? So typically we don't actually need to do any bounds checking whatsoever in our internal implementation of for each while. So that's the happy case. And as I said, in most other cases, compilers can optimize away our bounds checks. Beyond that, you know, if you're doing anything even vaguely expensive in your loop, then the bounds checking is basically just noise, right? So even if the bounds checking cannot be removed, then again, in many cases, it doesn't actually add any measurable overhead. But what about corner cases? What about those cases where, you know, you've profiled and you're like, Tristan, this is really annoying. I want to use Flux, but I just keep seeing this thing, this Flux bounds check coming up. What can we do about it? Well, in the cases where bounds checking does lead to unacceptable overhead, there is another function, read@unchecked. And what this does is it performs element access, but without additional checks. So all of the built-in implementations or provided implementations of the Flux protocol provide this overload, this unchecked read@. So this is an unsafe function, right? Potential UB, doesn't do any checking. This is the equivalent of like just the square brackets operator for vector, right? So if you profile, if you measure, and you see that, hey, bounds checking adds an overhead here, you can call the read@unchecked function instead. But, you know, always measure. And as I say, this is kind of the equivalent of like an unsafe block in other languages. Something to be used selectively because you need the absolute maximum performance. Okay, so that is it. So Flux, as I say, as I've been talking about, C++20 library for collection-orientated programming. This is a term courtesy of Connor. It can be used everywhere C++20 ranges can be used. So it supported GCC 11.3 and onwards, Clang 16, MSVC 2022, works with all of those. Can be used anywhere that C++20 ranges can be used. Offers, I hope I've managed to convince you, much improved safety, easy to use APIs for both producers and consumers, STL compatibility, and in many cases, better performance or better code gen than equivalent ranges code. So that's it from me. A few minutes late because we started a few minutes late, but thank you very much.